Right. So in this problem, you're going to find that the similarities are very much the same, even though the growth is in a different direction. So this is a radioactive decay problem, and so the decay of a radioactive element can sometimes be used to date events from Earth's past. In a living organism, the ratio of radioactive carbon, carbon-14, to ordinary carbon stays fairly constant during the lifetime of the organism, being approximately equal to the ratio in the organism's atmosphere at the time. After the organism's death, however, no new carbon is ingested, and the proportion of carbon-14 in the organism remains uh, in its remains begins to decrease as carbon-14 decays. Scientists who do carbon-14 dating often use 5730 for the number of years of its half-life, specifically carbon-14 half-life, and find the age. So find the age of a sample of which 10% of the radioactive nuclei originally present have decayed. Yes, that's what the question is asking us to do. So just like the last time, in the last example, we're going to use y of t is equal to the amount of material of whatever it is, population. In this case, it's the amount of carbon-14, and that's left after it's been radioactively decayed for some time t. We know that for 5,730 years, the amount of material that was originally there is half the amount. So I'm just showing you that the a's are there, but they will cancel out. And so we'll use this to determine, this will give us the k that we're looking for. So just like the last time, we need to know what the constant value is, the growth constant for this population. So we'll use that. And then we also know that y of, was it some time? Yeah, we're looking for the time again. So sometime, um, time of pop, the amount of material, it said it had 10% of it had gone. So uh, we left with, if there was 100% and we are missing 10% of it, that means 0.1 of the amount of it is gone. Of A is how much we have E to the KT. So this is actually what we're going to be solving for. Uh, this is 1 minus 0.1, so we can actually say that that's what, zero point 0.9 A equal to A E to the KT. I use A more often than why not, but realize that A and why not are the same for me. So this is what we're solving. So we just need to solve for this K here using this half-life information and then plug that back in here to find for the time. Okay, so that's what this problem is really boiling down to. So again, notice that this is not asking us to solve a differential equation. It's really just asking us to solve for the constant K and then solve for some time. Okay, all right, so let's go ahead and solve for this K. So K is going to be given to us by 1/2 A equals A e to the 5730K. The A's cancel out. And again, I'm going to take the natural log of both sides. Natural log of 1/2 equals, and this material is just going to come down. So 5730K. Now, like I said last time, notice that natural log of 1/2 here, the growth of, or the graph of natural log of t or x, whatever it is, looks like this. And so at this point right here, this is 1 comma 0. So whenever the natural log of 1 is equal to 1, or not the natural log of t is equal to 1, uh, then you're going to have 0. Okay. So if t is greater than 1, you're going to have some sort of growth. And if t or x, whatever that it is that you're measuring, is less than 1, okay, that means that you have a decay. And our, as that down here at 1/2, so our k, this is a negative number, which you would expect if it's a radioactive decay or the population is decreasing. Okay, so I'm going to divide by 7 here, 5730. So that reduces to 1. So that gives us the k. It's natural log of 1/2 divided by the half-life time. I'm going to leave it in this form. Again, it's some decimal number. It's negative. I use this to check that it is negative if it's a decay problem. That's what I would expect. And it's definitely going to be some small decay. Uh, we'll calculate that in a second. Okay. All right. So let's go down here to solve for this one. And just like in the half-life calculation for K, the original amounts don't matter. And we're going to solve for this time too. We know what K is. It's this number here. Okay, so I'm going to take the natural log of both sides, natural log of zero point 0.9. Now notice that natural log of zero point 0.9 is less than 1, so this is actually a negative number. Okay, equals, and then here, the natural log of e is just going to leave this top part, so it's going to be kt, and I'm going to divide by k. But again, k is also negative, so both of these two are negative. So sign-wise, this checks out. Okay, but dividing both sides by k, this tells me then that the time is equal to natural log of zero point 0.9 divided by this number. This number is negative, uh, like 1.2 times 10 to the minus fourth, something like that, roughly around there. Okay. So plugging both of those numbers into the calculator, you're going to get that this is roughly about 871 years. Okay. All right. So that is the solution to the second example. I hope that was helpful, and I'll see you in the next video.